Am I audible?
Hello.
Yes, sir. Okay. So, sir, we are going to start. So, a very warm welcome to the AICT sponsored Atal FDP. Thank you for joining us. It is my great privilege and honor to introduce today's second speaker, Mr. Lakshya Priyadarshi, an eminent expert in the field of quantum computing. Uh, Mr. Lakshya Priyadarshi is the Vice President of Quantum Platform and Solutions at QpiAI India Private Limited. At QpiAI, he leads the quantum software platform and solutions vertical, overseeing the development of QpiAI's quantum computing as a service platform and the complete quantum software toolchain for QpiAI Indus and Future System. He manages a team of over 20 scientists and engineers delivering quantum solutions for industries. Uh, Including pharmaceuticals, life science, automotive, manufacturing, financial services, and energy. He has led the development of QpiAI Quantum, a comprehensive quantum development platform, QpiAI Op, an optimization platform applied in the automotive sectors, and QpiAI Pharma, a drug discovery platform deployed by leading global pharmaceutical companies. He is also responsible for advancing full stack quantum system optimization and quantum algorithm development at QpiAI. Prior to QpiAI, Lakshya contributed to the development of QSIM, India's first indigenous quantum simulator. During his research internship at the Indian Institute of Science, IISc Bangalore, earlier at the Harishchandra Research Institute, Prayagraj. He worked on the mathematical foundations on quantum information. Laksh holds a BTech in computer science and engineering from the Institute of Engineering and Technology, Lucknow. He has published two research papers and has filed seven patents in the field of quantum computing. Thank you so much, sir, for joining us. Now, over to you, sir.
Hello, all. A very good evening to you. And thank you, Dr. Mukesh, for the very kind and generous introduction. So, to begin with, today's this session is about quantum machine learning, and uh, I'd be covering several aspects of how quantum computers can be used to develop machine learning systems, either on hard combinatorial problems or problems of interest in materials and chemicals domain, etc. And we'll also take up a simple example of how we can use the basics of quantum circuits to build a trainable model. So at this point, I am assuming that you are already familiar with what a quantum circuit is, what are qubits, and what are gates, and I will build on top of it. Uh, before I start, I would say that we are doing a lot of interesting work in the domain of quantum machine learning, specifically in the real world industry applications. And if you are interested in exploring further, it would be great to connect. With that, I will start sharing my screen. You can confirm if my screen is visible, then I'll begin.
Yes, sir, it is visible.
Okay. Thank you for confirming. Quick introduction to the organization that I'm representing. My name is Lakshya, and I am from QpiAI, which is a company based in Bangalore. And we are the only company currently in the country that is building quantum computers. and using our quantum computers to discover and enable real world applications, working with several academic institutes, research institutions, and with industries. And we are a technology rich company. We have several awards to our recognition. And primarily, we are engineering and scientific team. What you see on the left is quantum computer. This is housed in our Bangalore lab, and this is the only large scale quantum computer in the country, currently at 25 qubits, and also the most powerful one. And we have built the entire system stack on top of this quantum computer such that it can be leveraged by researchers and faculties that are working on real applications of quantum technology. We also have certain domain specific software tools like in the domain of optimization, chemistry, material sciences, etc. So, what you see on the screen is an example of the software which can be used to develop quantum algorithms and quantum circuits. And on the left, what you see is the breakdown of the complete stack of how we have built our system and how actual quantum computing stacks are built, all the way from the processor to the algorithms. And since you already know about quantum circuits, qubits, and quantum gates, we are in a good position to start learning about or discussing about quantum machine learning as a technology. So the very first question that we would like to ask ourselves is why look at a new form of training algorithms that can learn from data? And the answer lies in the fact that over time, as we are seeing, that all kinds of data, whether this is consumer data or scientific data, experimental data, or data from digital platforms, banking systems, healthcare systems, all kinds of data and in all forms of modalities is increasing, and it is increasing exponentially. In fact, the amount of data that we create in a year now is almost close to half of what we have created in the entirety of data storage and digital technologies. So data is growing at an exponential pace, and we need new forms of learning techniques to learn from this complex data. Second observation that we see is as we have better and larger AI systems built on deep neural networks, over time, two trends are very clear. Trend number one is that what you see on the bottom right, as these systems are becoming more powerful, the degree of parameterization of these models is increasing, and it is increasing vastly. So it's very common today to have a 100 billion parameter model or 200 billion parameter model, 10 billion parameter model, etc. So today's deep neural networks are heavily parameterized. And the second observation is that the amount of computing resources that are required to train those models are also growing in terms of the capacity or the flops, the floating point operations per second, as well as the total number of such compute resources that are required. So the volume of compute resources are already also increasing across all kinds of, let's say, academia, industry, uh, collaborative research domains, etc. So because of this observation, where the data complexity is growing and the compute resources are also growing, and having the understanding that this compute and data and the models that learn from that data are the backbone of modern AI. At some point, this technology is getting saturated and it cannot solve some of the problems that may be of real practical value. I'll give certain examples. Example number one is about designing new medicines and novel drugs from the chemical data that is available. Now, it's a hard task to do. It takes enormous amount of money and capital resources to discover new drugs, close to a timeline of 10 years and approximately $1 to $2 billion for a drug to come to the market. But if we can create efficient ways of learning from the chemical data, and instead of having lab experimentation on real chemicals to synthesize a drug, if we can simulate that, that would save a lot of resources as well as accelerate the discovery and ultimately impact the society. Similarly, we can translate the same idea to other domains such as chemicals, materials, detection of fraud in financial systems, or efficient management of traffic and large scale transportation, etc. So, the entire chain of the current AI or machine learning world will be impacted by quantum, and that's why it becomes essential to learn about this kind of novel technologies. For today, specifically for this session, we will focus on how to build a quantum machine learning system, or a really simplified algorithm. But the intent and the aim is to go through the very fine details of how this basic system is built, so that in future, when you need to work on more complex and sophisticated quantum algorithms and quantum machine learning systems, you can use these as basic building blocks and proceed ahead. Apart from that, there are considerations about energy requirements of classical AI, and the limitation of having not having adequate or enough amounts of training data to train AI. And where quantum computing come in is they can use the quantum computers can use their parallelism to encode and represent complex data. The modeling techniques can represent high dimensional data and build high dimensional AI models. And quantum algorithms can be developed that can use the quantum parallelism and quantum modeling techniques to perform tasks on pattern recognition as well as generative systems. So, using this as a backbone and this as the foundation of how to build quantum machine learning systems, they can in turn be applied to solve classically intractable or hard problems in a more efficient way. They can also enhance classical AI with new forms of models and computes. They can make supercomputing faster and energy efficient for very specific kinds of tasks like weather modeling, bioinformatics, genomics, chemical sciences, financial systems, etc. And using all of this, it would accelerate scientific discovery and also accelerate large scale optimization that is used in industrial operations and decision intelligence. So now we are starting with quantum machine learning, and see what happens when we are processing information on a quantum computer. It's useful to contrast it with how we perform the classical computation, right? So let's say that we have our input over a 7-bit um, data vector or a bit stream. Now, this input of the classical bits will need to go into a classical computer, and the classical computer will execute an algorithm, which will be a classical algorithm. And under the hood, they will be represented by digital logic circuits in the form of Boolean inputs. And after this bit stream input is provided to the computer, it will do the processing and give the output. What changes in a quantum computing system is that instead of providing the bits, we are encoding our data and the overall input into the space of 7 qubits. And as you already know, that qubits can exploit parallelism. Hence, multiple basis states can be represented as a combination. The final state will be a combination of these basis states. And this entire input in its parallel state will be given to the quantum computer, which will execute a quantum algorithm. And these quantum algorithms will be represented by quantum circuits. So that is the basic idea of how it differs from a classical algorithmic flow. Now, when we talk about applying this flow to the machine learning domain, there are certain possibilities that can happen. Here, I was talking about the data on one hand, which is in the form of our data or the inputs. And the second point is around what algorithmic systems and computers we are using to execute that data. So, the kind of possibilities that exist here is you can see through these four quadrants. On this side, we are discriminating on the basis of the type of algorithm, right? So either it could be a quantum algorithm or it could be a classical algorithm. In the same way, on the horizontal axis, we are discriminating on the basis of the data that is being given to the algorithm, right? So there are scenarios where within the domain or within the context of quantum machine learning, where we operate on classical data and we operate using classical algorithms computing. And these kind of algorithms are called quantum inspired machine learning algorithms. That is the first quadrant. Uh, Really important subfields of quantum machine learning, and you should definitely explore it because several applications in better interpretable AI or explainable AI, as well as their applications in natural language processing, into generative AI and the compression of large language models, etc. These all are quite relevant to the first top left quadrant. The second example is with respect to having a classical algorithm perform computations on quantum data and having the machine learning system do those kind of training protocols. The third example is to have a classical algorithm being applied, a classical data being applied onto a quantum algorithm. And this is the most common type of quantum algorithms that you may see in tutorials, in research papers, or in the ways in which new quantum algorithmic techniques are being explored. Because the classical data is abundant. And because quantum bits or qubits can efficiently encode high dimensional classical data, because of that, this line of work is really quite popular. So in this example, what you see is the input vector is an image and it is being encoded into the state of a qubit. Finally, there could also be scenarios where you would have quantum data and quantum algorithms, and you are directly building machine learning system on the quantum data using a quantum computer. That is the most advanced form of quantum machine learning. It's only picking up as more powerful quantum computers are becoming available. One of the good examples of this technique is to directly encode molecular data and train a quantum circuit from the data or on the data of this molecular system, right? So one of the good examples is you train a big library of different molecules, hundreds of thousands of molecules. You use their quantum data and train an algorithm on a quantum computer, and it can be used to predict properties of those molecules, or design better molecules, etc. So, this is the broad classification of how we see quantum machine learning, and uh, exactly from here, different applications come up. Now, to map our picture of the four quadrants to the data or the type of learning task that we need to accomplish, we need to connect it with the type of learning algorithm. It's like supervised learning, unsupervised learning, and reinforcement learning. And similarly, new forms of learning like semi supervised learning as well. So, what I would highlight here is that just as we have different types of learning tasks like classification task, regression task, generative task, all those types of tasks can be tackled with quantum machine learning, where the supervised learning algorithm could be a quantum algorithm, the unsupervised learning algorithm can be a quantum computer, or even the reinforcement learning algorithm can be a quantum algorithm. And naturally, after a pipeline of a machine learning system is built, it can be used across various kinds of applications like in chemical sciences, into image and computer vision, into power systems, utilities, and electrical networks, into the domain of logistics and transportation or manufacturing, in the domain of financial services or capital markets, and finally into healthcare and life sciences. And these are not the only applications that are possible. In fact, because of the generalizability of these quantum machine learning algorithms, it can be applied to various other domains as well. So, now I'm going to talk about two types of quantum machine learning techniques. And I'm calling the first type of quantum machine learning techniques as quantum machine learning generation 1. And this generation 1 of quantum machine learning is heavily based on exploiting the similarity of the mathematical formalism of quantum mechanics and quantum computing, which is linear algebra, to the mathematical formalism and the structure of how a machine learning algorithm is built, which is also using linear algebra in most of the cases. So that's the idea. If we can encode our data into these linear algebraic spaces, which in the context of quantum computing will be large exponential spaces, then we can try to derive some advantages because of the parallel power of quantum computing. And we can also use the entanglement as a resource to model some complex correlations. Interestingly, many of these techniques have been developed over the last 1.5 decades and have given promising results in the context of fault tolerant quantum computing. Right? So, when we have error corrected quantum computers, many of these algorithms will be really efficient and can solve large scale machine learning tasks, especially in the context of sampling, optimization, and search based techniques. So, these are some of the quantum techniques like quantum based linear algebra or HHL algorithm, search based techniques, sampling techniques, as well as ground state optimization. And on the third column, you see its corresponding uh, application in the context of machine learning. The last column is the different algorithms that so far people have developed, which can be applied for these applications using these different techniques. Right? So, examples like quantum support vector machine, quantum principal component analysis, quantum k means clustering, etc. So, what is common across all these different algorithms is that we will be using the quantum circuits to encode data. We will be using these gates to create algorithms, And these algorithms will leverage the high dimensional or the exponential spaces of quantum computing, and can do some of these linear algebraic operations more efficiently. So this is about QML generation 1. Um, Let me skip this and I'll come back to it if needed. And QML generation 1 actually deals with these three features of limitations of classical machine learning. They help us build training models on high dimensional data or high dimensional feature spaces. Because of the exponential nature of Hilbert spaces, these quantum machine learning kernels are highly scalable, as opposed to classical machine learning kernels, which are not as scalable. And quantum computing techniques also help us in escaping local minima in complex optimization landscapes, which is a problem in classical machine learning, where this energy based optimization or the complex landscapes of machine learning algorithms cannot be navigated effectively, and the system gets stuck in a local minima. So these three challenges for classical machine learning, they sort of give an advantage in quantum machine learning, all because these quantum systems are natively operating in exponential spaces, and in these exponential spaces we can encode the data and the features, and these become quantum enhanced feature spaces. Now I'm going to talk about the second generation of quantum machine learning. Earlier, I had talked about the very first generation of what has been developed over the last 1.5 decades or so. But what started in mid 2014, 2015, and close to 2016 is a new wave of quantum machine learning algorithms started to emerge. And the idea of these quantum machine learning algorithms was strikingly similar to another emerging domain at the same time, which was deep neural networks. So the second generation of quantum machine learning algorithms work in a way which is very similar to deep neural networks. And how we do it is by encoding the data onto a quantum circuit and constantly changing the values of data in the circuit, because we make the circuits trainable. What do I mean by making the circuits trainable? Okay, you have already learned about various kinds of quantum gates, and you are aware that these gates are applied as rotations on the qubit. Now, let's say that every time I'm applying a gate on a qubit, or I'm applying the rotation on a qubit, the angle of rotation is based on certain parameter that I can change. Now, what happens is if I control the parameter, I can control the output of the quantum algorithm. And the way we use this in machine learning, so on the left, you see a parameterized quantum circuit where the unitary operator is parameterized by the vector theta. The way we use this in quantum machine learning is we calculate based on the state or based on the results from the quantum circuit, we calculate a cost, just like we do it in our deep neural networks. Now, the cost is based on the parameter theta because the output is based on parameter theta. Then we transfer this value of the cost and the theta vector onto a classical device which does optimization in the theta space. And depending on the distribution of my data, and depending on what kind of learning task we are doing, and depending on how we are defining the cost function, based on all of that, we can keep on iterating this process and keep on updating the vector theta until we get a really good approximation of the map that we are trying to create using this quantum algorithm. Now, a natural question to ask is we were doing the same things using deep neural networks also, right? It's exactly the same structure. We are passing in the data to the neurons. We are using activations, we are using different kinds of transformations, doing backpropagation and updating the theta vectors in neural networks as well. What is special here? So, what is special is the fact that these qubits they can encode exponentially larger or denser representations of data because of Hilbert space. And since any unitary operation on a qubit is reversible, and we can apply any rotation on the block sphere, the action space or the operation space is quite dense, and we can do effectively really rich operations in lesser number of gates. That is the basis of the new generation of quantum machine learning algorithms. So if we compare classical to quantum ML, in classical machine learning we have vector spaces. In quantum machine learning, we encode the data onto Hilbert space, which is a complex vector space. The features are encoded in quantum amplitudes, though they can also be encoded not only in amplitudes but also in phases, in the angles of rotation, and a few other techniques. But the most common one is to encode in quantum amplitude. Instead of applying the activations, we are applying measurement operators to introduce nonlinearity. And just as we have the concept of kernels in classical machine learning, we replace it with the idea of quantum feature map, and it becomes a quantum machine learning algorithm. Uh, I will take a quick pause to check that if you are hearing me, am I audible and all good?
Yes, sir, you're audible.
Okay, great. So I'll continue from here.
Yes, sure.
So far, I was going through a story, and the story was about quantum machine learning. Why do we use quantum machine learning? What are the motivations, and what different kinds of categorizations of quantum machine learning we can do? Now, I will start with a really simple example of building a quantum machine learning algorithm. And I would encourage that if possible, you can work along with me and understand this algorithm using some pen and paper based method, calculation, or whatever you call it, and look for yourself how this algorithm is built. And we have chosen a very simple task to demonstrate this machine learning algorithm or quantum machine learning algorithm. The task is to do binary classification of data points that reside in two dimensions. What it means is that our data points, which are basically a vector x, demonstrate described by its components x1 and x2, it resides in the real space of two dimensions, and the label or the I can say the output for that particular vector would either be 0 or 1. So you see that this is a discrete set, and we have to select either 0 or 1 for a particular vector. Hence, it can be treated as a binary classification problem. We'll create a really simple data set. Basically, we will have a few points on a 2D plane, and we will have a really simple classification boundary also. This is how we will describe the classification boundary. If x1 plus x2 is less than 0, we will term the output as 0. If x1 plus x2 are greater than or equal to 0, then we will turn the output as 1. So it's a very simple linear classification boundary. Now, what happens in just you can ignore the other text, but only focus on this block diagram. What happens when we try to build an algorithm for the problem that I just described? Now, typically, this data will come from a real world use case. Right now, I'm demonstrating a really simple scenario, but in your research that you do, or maybe you would be using quantum machine learning to do some research for your domain of area, for your area of expertise. There, the data will come from a real use case. Now, it has to be really efficiently mapped to quantum data, and thereby creating a quantum based model which can then be treated using either a quantum algorithm or a hybrid quantum classical algorithm. So you have to work across the stage of each of these building blocks to create an end to end pipeline of quantum machine learning. In the context of the problem that we are trying to solve here, these building blocks would be to train a quantum machine learning algorithm to achieve this kind of a classification boundary. That will be our aim. How we will do this is we will use quantum states to encode the data. Quantum states are nothing but the qubits in this context. We will apply unitary transformations. Often they will be parameterized unitary transformations. And finally, we will perform measurements to get the final results. And iteratively, when we do this, we can create this as a learning algorithm. And the main tools that we need here are ways to encode our data onto quantum circuits, ways to parameterize the quantum circuit, perform measurement, and then use this setup to iterate on the parameter space by a classical optimization loop. In terms of the actual steps that will be performed to build the quantum machine learning algorithm will be something like this. In this example, we are taking the case of a variational quantum algorithm or a variational quantum classifier, which means that the principle of variation will be applied here, which is nothing but using the quantum state parameterized by theta and cause a variation in the parameter space by iterative optimization and find across those variations find the most optimal value of theta. So what you see here, point number 1 to 7 is the flow of developing a quantum machine learning algorithm in the variational regime. You have the classical data, you convert the classical data into a quantum state by applying a data encoding, you parameterize the quantum circuit, and there are various strategies to parameterize the quantum circuit based on your use case and based on the problem that you're trying to solve. You will determine which parameterization strategy to consider. Then you'll have to define measurement and what types of measurement, in which basis, etc. And once this point number 1 to 4, this process is done, you have the setup ready. Based on the measurements, you will calculate a loss on some loss function. This computation will happen classically. And based on the current value of the loss, you will feed it to a classical optimizer, which will run on classical computer and generate an updated set of theta vector. And this goes on as a feedback loop until the system converges. Now, I would recommend that you really look at this diagram on the right and compare it with a deep neural network. It's very similar. The first block, you have the embedding stage or the encoding stage. Then you have various sets of transformations here in the form of gates, what you see. Similarly, in the neural network, we have some transformations. And finally, we do the measurement, which is used to introduce activations inside our system. Then we measure the loss using a loss function and do classical optimization, which is very similar to the way we do back propagation in a neural network. This is something that is already known to you, but I'm still referring to it, which is as a refresher, that we represent the qubits as vectors, and we use these matrices x, y, and z to perform gate operations. We will be using the rotation gate, which is rotation along the axis alpha by an angle theta, and we will use this property of rotation to parameterize our quantum circuit. Explicitly, for example, rotation by an angle theta along the y-axis is described by this matrix. So now we are starting to build our quantum algorithm or the quantum machine learning algorithm. The very step one is to encode the data and create a feature map. What data? I'm referring to this data. The data that is our input, or which describes the distribution of or the classification that we are trying to do. There are various encoding strategies, as I had mentioned earlier. We can encode the data in amplitude of a quantum circuit. We can encode the data in the angle of rotations of a quantum circuit. We can encode the data in the phases, and we can also use a combination of these different techniques to encode our data. In this very simple example, we are using the angle encoding. And since we have two values to encode, we are applying two successive gates. One is Ry. So initially, we are applying Ry by the angle value given by x1, and then we are applying Rz with the angle value being the value of x2. As you already know, this represents the operation of a unitary gate or a unitary operator onto the state of a qubit, which is get 0 in the beginning, and then these gates are being applied. What happened here is that the values of x1 and x2 are now encoded into the state of the qubit vector after completing this transformation or after completing the calculation of this transformation. So our encoding step is now completed, and the output of the encoding step, which is this part, ket of phi x, this is called the feature map. Just as we have a classical feature map, this as a feature map now resides, the quantum feature map now resides in a Hilbert space or a complex vector space of higher dimensions. The second step is to create a quantum circuit which is parameterized, and those parameters can be used to make the circuit trainable and classically optimizing within the space of those parameters, such that we can say that we are learning those parameters. So we are here choosing the circuit to be described by a unitary U parameterized by the vector theta, and the components of the theta vector are theta 1 and theta 2, these two values. And the rotations that we are applying are Ry and Rz. So what happens now? We have already created a feature map in step 1. In step 2, we have defined the unitary operation that needs to be put on the quantum state. We'll now perform the operation, which is on this state, apply this operator. And that would be called as phi out, which is the output state vector. And this generates this sort of a trainable quantum circuit, right? So far we have done this part, the one of creating the circuit. Next, what we would do is we will perform the measurement. You may already know through the FDPs that the measurements are typically done by calculating expectation values, and the expectation values will be calculated through this form, where we take the ket vector, multiply it by the particular measurement operator, and then we multiply it by the bra or the row vector. And to calculate the probability associated with that particular outcome of y is equal to 1, we use this formula, which is 1 over expectation value of the state by the operator z by 2. In case if you are wondering why this particular formula, this basically comes from the fact that the probabilities should sum up to 1, and the probability corresponding to y is equal to 0 will be 1 minus the expectation value over 2. So that is how the probabilities are calculated. Once the probability is known, we can use the very well known and well defined binary cross entropy loss function to calculate the loss at this particular point. And using this loss as an indicator, we will continue to update our theta vector until this loss converges or this loss decreases towards a minimum. So that is the strategy of building a quantum machine learning algorithm and using it to train over a distribution of data, and then use it to make some predictions. So as a graphical example, this is something similar to what we have done. We had the data set of the vector x. We can choose to do either amplitude encoding or block encoding or angle encoding, phase encoding, etc. Whatever. In our case, we had chosen angle encoding. After the encoding is done, a parameterized circuit is created. Measurements are done. Expectation values are calculated. Using the expectation values, the cost function is calculated. Based on the value of the cost function, we pass on that information to an optimizer. And what the optimizer does is keep on changing the values of the vector theta, or keeps on updating theta until we converge. So that is the high level structure of a quantum machine learning algorithm. Right now, what we are going to do is we will program a basic, simple, very same example that we have discussed, and we will see how the quantum machine learning algorithm trains. A final point on how this compares to the algorithm that we had just created. How does this compare to a classical deep neural network? We know that classical neural network applies various linear algebraic transformations. In the same way, a quantum circuit applied the embedding method to encode the data. The model here was using a unitary operator to evolve over the state. Nonlinearities, you may know that all of the unitary operators that we apply Quantum mechanics, by its very nature, is a linear theory, and quantum computing is a linear operator based method. So, one of the things that are very natural to ask yourself is, how do we introduce nonlinearity? Nonlinearity in quantum algorithms is introduced by performing measurements, because the outcome of a measurement is inherently random and you don't know whether it goes to 0 or 1. So, it creates a nonlinear nature. The optimization over the parameter is happening by the parameter shift rule, which is essentially this point that I had mentioned. And the real advantage here comes in because, unlike a real vector space of n dimensions, we are operating in a complex Hilbert space of 2 to the power n dimensions. This was a very simple example, but more sophisticated, more complicated algorithms can be created, like quantum neural networks, quantum kernel methods, example being a QSVM, a variational algorithm, quantum Boltzmann machines, quantum reinforcement learning, and a whole lot of other techniques, including supervised, unsupervised, and reinforcement learning. Before we proceed ahead uh, to the demonstration of a simple example, I'd like to summarize all of this and conclude the theory part. So, point number one that we have seen is the need of quantum machine learning, because there is a growth in data both in terms of volume and also in terms of complexity. There is a saturation of classical computing resources, and also because some problems are inherently quantum, they require a quantum learning method. That is why we need to build quantum machine learning algorithms. We typically categorize it against the quadrant of classical data and quantum data versus classical algorithm and quantum algorithm. And that gives us a four quadrant kind of categorization. Then we have seen the basic building blocks of building a quantum machine learning algorithm, like the encoder, the trainable circuit, the measurements, and the classical optimizer, and a feedback loop over it. Please note that there are other types of learning techniques as well, and to understand them and to learn about them and to work on them, it's not possible to cover it all in this kind of a session. But it's a big field, it's one of the most advancing research fields in quantum computing, and I would encourage you to look into the details, and look into how these other families of algorithms are created and apply them onto your own field of research and even teaching for that matter. And how we can work together on this is by you using our quantum computer to run these quantum machine learning algorithms, or using our SDK, which have various models and libraries like these already implemented. And it's quite easy to transform your data from your domain. This could be agricultural data, healthcare data, medical data, could be financial data, it could be data from some image source like remote sensing, satellite imagery, it could be from factory floors, right? So, computer vision based data. It could be several domains like telecommunications, it could be logistics, transportation, um, weather modeling, ocean engineering, anything that you can imagine of. Transform the data and use really optimized libraries that we have built to directly encode that data and ingest the data, build quantum machine learning algorithms, train them using simulators. We have built simulators that can run on small scale machines. We have also built simulators that can run on high performance computing machines. And of course, the models that you create can also be run on the quantum computer, which I had shown you earlier in terms of the 25 qubit quantum computer. So much of these application stack is already built in. Your quantum machine learning libraries are already built in. You can experiment with different types of quantum machine learning algorithms and use it to discover new applications, start really new and, in fact, novel areas of research and development. And the results, of course, since it is executed on a quantum computer, can be used for benchmarking analysis, projections, and theoretical analysis, as well as experimental uh, analysis. So that being said, there are various kinds of quantum machine learning systems. Just like we have deep neural networks for image data using classical convolutional neural network, similarly, you can construct a quantum neural network as well, which acts as a convolutional filter. So, just as you have a classical flow of having an image input, applying convolution operators and pooling operators, similarly, you can apply the quantum circuits, which are very special, created in a very special way, such that they can act as a convolution filter or as a pooling operator. But what advantage do we get? We get the advantage of exponential feature spaces. We get the advantage of really dense representation of data and unitary operators. So there could be CNNs, there could be GANs in the quantum machine learning domain, there could be autoencoders, and whole lot of things. In fact, in the recent years, people have also started developing quantum transformers and natural language processing using quantum algorithms. So the possibilities are many, and I would encourage you to explore it further and develop some of your own algorithms and apply it to your own problems and take it towards publication or novel intellectual property. So I will now take a pause and go ahead to demonstrate the training of this quantum neural network or a variational quantum classifier for this very simple problem that I had created. The whole point here is to show you that this kind of a system can work, and then later on you can extend it to much more complex and sophisticated algorithms. Since this is a very simple example, I have not used any library like Bracket, Circ, or even our own library. We call it as a QpiAI Quantum SDK and a QpiAI QML library. So we have our sets of libraries. But for this demonstration, I'm not using any library because this is very simple, and you can actually look inside the implementation since it is all done on NumPy, so that it becomes really clear to you as how these steps are implemented. And later on, you can work towards use of really optimized and specialized libraries to discover applications and apply it on your own tasks. So with that, I will take the very same example of what we have talked about so far and do a code level implementation of this particular setup. So I would just like to confirm once if you are able to see the other screen that I have started now.
Yes, sir. Yes, sir.
Okay, great. And we have time until, so Dr. Mukesh, sir, we have time until when?
Up to 7:30.
Okay, great. So I will complete this by 7:15.
Okay.
and then we can take up some questions if there are.
Sure, sure, sir.
So this is a code level implementation of the problem I had just described earlier. We will be creating a data set of a few points on a two-dimensional plane with binary labels, which will mean that y is either 0 or 1. We will encode each data point into a single qubit quantum state, and that will be our feature map. After creating the feature map, we will apply a unitary operator to that quantum state, and that unitary operator will be parameterized by theta. Hence, we can call it as a trainable or a variational quantum circuit. We will calculate the expectation value by operator z, and using the expectation value, we will get a probability as we calculated earlier, 1 plus expectation value over z by 2. Having this setup, we will iteratively use this to train on the data that we have and use a hybrid quantum classical loop to do the optimization epoch by epoch. And this will be a very basic example for us to look into how this quantum machine learning system works. Very first point is to install the libraries that we need, which are nothing but numerical Python, NumPy, Matplotlib, and Qtip, which is a specialized quantum um, systems library for working on open quantum systems. It is not much relevant for the domain of quantum computing, but still I have used it because I will use it to visualize our quantum state. Okay, so the very first step is to create our data set and use this as the classification boundary. So we are creating a data set here of these 4 points, and this is point number 1, this is point number 2, this is point number 3, and this is point number 4. And we are mapping the first 2 points to the label 0 or category 0, and we are mapping the other 2 points as category 1. So it's a binary classification by definition. And we can see this in the vector form as well, uh, as a numpy array. So this is our data set, and this is our labels. If we need to plot this system, it will look like this. We have 4 points. This is the classification boundary that we have drawn as we had defined earlier here. And the blue points are the class 0 and the orange points are the class 1. So you see it's linearly separable. It is a binary categorization, and now we will build a classifier for this system. To do that, we need to get the basics first. So what we are doing is, just as we had seen earlier, the definition of our rotation gate. Through that, we are defining the rotation along y-axis. What happens here? This is where we are defining the matrix, the rotation matrix. Similarly, here we are defining the rotation around z-axis. After creating the implementation of the rotation gates along y and z-axis, we are creating a single qubit state, which is representing ket 0. As you already know, our ket 0 is represented by this vector 1 and 0. So that's what is created here. And we have created the poly z gate or the poly z gate as it is written in its matrix form. Just to have a quick check, we have calculated ry of pi by 3 and rz of pi by 3, and it is equivalent to substituting the value of theta as pi by 3, and we get these values in the matrix. After creating our base setup, which is creating the data set and creating the operators, we are now creating the step to encode our data into a quantum state. And as we had seen in our presentation, we were defining the quantum feature map like this, providing inputs to the rotation gates in the form of values x2 and x1 as angles. It may be possible that the order of rz and ry may have changed. So you can consider either of the two depending on how you're designing the algorithm. It's a change in the design choice. So I'm executing this. Firstly, what we did is we defined a function to encode the data, which will take our vector x and create the feature map based on the transformation that we had already defined here. As an example, we can see that we are taking this particular vector. Its components are being mapped to these numbers x1 and x2. And the value of the vector is sent, and finally the output that comes in is this state with the encoding. You must already recall that it is mandatory for a qubit state to be normalized, right? So here we are verifying that if we calculate the norm of this encoded quantum state vector, it is 1. Because of a computer floating operation precision, it is 0.9999 and so on. But in terms of absolute value, it will be equal to 1. So this is our encoded quantum state vector. After we have created the feature map, which is our phi of x, we will be creating the quantum circuit, which will be used to train on the parameter theta. And we call it as a variational circuit, where the circuit is parameterized by theta, or it takes the input as theta, the theta vector. And the components of this vector theta, which are theta 1 and theta 2, we are applying as angles in this rotation gate. So we are calculating ry of theta 1 and rz of theta 2. This is our variational circuit, very small variational circuit. Now let's see how we can use it. We generate a random theta and use this as the initial point of our vector, and we supply this theta to the variational circuit. And the matrix for that variational circuit will be something like this after the application of theta angle. Now we need to perform the final part of whatever system we have built so far. We will apply it sequence by sequence to encode the data, apply the feature map, apply the model, then measure the expectation and calculate the probability. So that is what happens here. We take in the input x and theta, create the quantum circuit or the variational circuit, and use this to predict the probability P. How do we do that? First, we calculate the quantum state, then we apply the formula to calculate the expectation value, and from the expectation value, we are finally calculating the probability. So, for the example of theta 0 that we had initialized, and the example data set that we had created in terms of x example, this is the probability 0.307. Finally, after we have calculated the probability, we can calculate the cross entropy loss based on the values of y, which is the label, and the probability. And as you already know, this is how the cross entropy loss is defined, which we know from our earlier knowledge of classical machine learning. So here we write functions to define a loss for a single vector. Then we iterate over all the vectors in the data set to calculate the loss across the data set. And by applying onto the dataset X that we have created, we can calculate the initial dataset loss before the model is trained or before the variation circuit is trained. Then we proceed ahead to train our variational circuit by using method of classical optimization. In this example, we are using a parameter shift rule, which is basically a method of using finite differences to approximate the gradient at a particular point. If you are well aware about these domain of how gradients are calculated and how we can use finite difference method to calculate the gradient, it's well and good. If you are not aware, then you can skip this point and just consider it to be a step action where we calculate the gradient based on the current state of theta. Now, this is the final function where we are training our variational circuit. So step by step, we can say that we will be supplying the data set X, the label set Y. We are just like we do it in our traditional neural networks. We are setting up the learning rate and the number of epochs, generating a random theta, creating a list to store different values of theta across these 120 epochs, and also creating a list to calculate the value of the loss function across each of these epochs. Then we iterate over each of the epochs or each iteration. We calculate the gradient. Then within that particular calculation step, we apply the method of finite differences and use the method of finite differences to update our gradient, which is basically we initialize it as 0 and then we update the gradient values. Using our update method or the update equation, we update the theta as theta is equal to theta minus learning rate into the gradient. After that, we calculate the loss function, and based on the loss function, we update the history of theta and the loss function value. At several checkpoints like the very first epoch, the 10th epoch, the 20th epoch, and so on and so forth, we are also printing the value of the loss. So what we would see is, using this very simple example, we are seeing that as the epoch continues, the value of theta will continue to change until certain point and then it will saturate. And also the loss will keep on decreasing uh, after a few iterations. Initially, it may have some oscillation because of the nature of training, but over time it will saturate and attain a minimum. Now, from your knowledge of classical machine learning, you should already recognize that this is not the best way to train a model, because we are considering only a few data points, only a small number of epochs, and the trend here is not too clear. But the aim here is to go by each and every detail of how a quantum machine learning algorithm can be built. And later on, you can experiment further and apply more sophisticated techniques to your own research problems. These are the visualizations of as the number of epochs continue, how the loss saturates by decreasing. Finally, we can evaluate the predictions of the trained model by predicting a label on a new theta that we generate, a new x vector that we generate. So that is the testing and validation step. And typically, this curve that you see, this is the boundary that has been created by our variational quantum circuit. So as you see, the variational quantum circuit is able to create a classification boundary between the blue points and the orange points. And as we have more number of points, as we have higher dimensional data, that's where the utility of quantum machine learning algorithm comes into picture. These are visualization of the states. So basically, starting with an initial state, then after applying the unitary operator, there is a change in the state, which is basically the initial state is zero. The blue one, and after the application of the with the encoding is the blue one, and after the application it becomes orange. So with that, I will stop here and just take 1 or 2 minutes to recap what we have done so far. We started with a basic intuition about what quantum machine learning is, why do we need it. Then we looked into a very basic example of building a quantum circuit that can be trained, using it for a quantum machine learning algorithm development. And we used simple numerical Python based programming techniques to implement it and train a quantum neural network or a variational quantum classifier. Now, this is just a starting point. The field of quantum machine learning is broad and vast. There are hundreds of techniques, hundreds of learning algorithms. The applications to which it can be applied to in the real world is also enormous. And there are various tools that will help you build this quantum machine learning systems. I would like to highlight our tool, which is what has been built by QpiAI. It's the QpiAI Quantum SDK. In fact, we work with several academic institutions to help enable the faculty members learn our SDK through structured training programs and be ready to execute some of these workloads and circuits on our quantum computers, such that later on, when you apply for projects under the National Quantum Mission or through other uh, forms of support through various departments like DST, DBT, uh, and agencies like MIT or state CST, you already have an experience of running these quantum circuits and quantum algorithms on a quantum computer. And our computer being based here in the country, in India, it enforces the data residency and the indigenous technology component, it retains it. And because of that, there is an advantage in terms of the end project being allocated. So, with that, I would encourage you to connect with me, and we can look towards ways of working together, not only in the domain of quantum machine learning, but also beyond that. We work across the entire domain of quantum computing and AI. So, I look forward to that collaboration as it can happen. But with this, I will conclude this session, and we can take one or two questions, and as per recommendation from Dr. Mukesh, and then we can wind it up.
Thank you, sir. Uh, okay, audience, if you have any question, you can type your question in chat box. So already we have some questions. Uh, there is one question from Habiba. Can you recommend any free tools or data sets for quantum key distribution?
So, quantum key distribution is one of the techniques that are used to transmit keys, and it falls within the domain of quantum communication at large. There are certain tools like NetSquid and um, certain tools from various groups in TU Delft that are available. You can check them out. On the contrary, what I would also highlight is that QKD is an active area of research, and even we are working on that domain to build efficient and optimal high performance computing accelerated QKD simulators that can be used to do various forms of analysis like fiber based QKD, free space QKD, analysis on the key capacities and the bit rate and all of those things, and analyze the effects of noise in our quantum channels. All of that is a really broad field, and even we are working on them. So it would be good if you are interested. We can talk further.
Yes, sir. Next question from Dr. Priyanka. How can we fairly compare quantum ML with classical ML based on performance, cost, and practicality?
So at the current stage, if you look through the literature, or if you look through all of the state of the art works that have been done in the domain across all of the leading groups in the world that are working in the domain of quantum machine learning, the idea is to discover algorithms that will give provable advantage either in the near term using hybrid techniques, or in the long term using fault tolerant quantum computing. So, in that context, the performance of quantum machine learning algorithm will exceed the performance of classical algorithms in various cases, like high dimensional data, really complex multivariate optimization, quantum data from natural or quantum sources, and applying machine learning on that. So these are some of the cases where, in terms of performance, quantum algorithm will excel. There are also some scenarios or use cases where classical algorithms and classical machine learning will excel, because quantum will be an overkill for that, and it can already be solved efficiently using a classical machine learning technique. For example, the linear classification that I was just talking about. In terms of practicality, it's highly practical for several complex data sets like financial data, chemical data, medicine data, etc. And in terms of cost, the idea of a quantum computer is to solve really hard problems that cannot be solved using supercomputing resources, right? So if you look at various supremacy experiments that have been done, Supercomputing running for thousands of years are definitely a lot more costlier as compared to running run workload on a quantum computer for a few seconds, right? So in the long term, quantum computing based solutions will drastically bring down the cost of really high value applications such as bioinformatics, weather modeling, drug design and discovery, material design and discovery, etc. So that is what my opinion is. Uh, you can look through various publications to compare where people have run experiments and compared the performance of classical and quantum algorithms, and that will give a better estimate and an idea about how on task to task basis the performances vary.
Okay, sir.
Yeah.
The last question from Dr. Harpreet. Adding quantum to neural networks increases complexity. Is increasing neural network complexity always the best solution, or can better physics-based features reduces model size?
Yeah, this is a great question. And what happens in real scenarios is, depending on the data set and depending on the technique, both these things work. So let me give an example. The deep neural network revolution that happened, that was an impact of large data being trained on really over parameterized models on very large compute. So over parameterization here was the key. You were using more parameters than what was needed to represent the characteristic of the data. But because you have an abundance of data and training it over again and again, the neural network was able to recognize patterns and store the memory of those patterns and the knowledge about the system in as many parameters. So, what happens in a quantum machine learning system and a quantum, let's say, a variational algorithm that we were seeing, because of the operations, because of the density of the operators, and because the algorithm is reversible, we can cut down on the number of operators that are required to perform a certain transformation as compared to a neural network. So that leads to efficiency in modeling the learning process. Second aspect is that the space of a neural network can be an arbitrary space. You can apply any transformation, but a neural network for a quantum neural network or a variational quantum circuit, you are constrained to use only unitary operators. That also reduces the complexity in terms of the number of steps that are required to execute the learning task. On the second point is this physics based intuition. This was extremely useful. Majority of quantum algorithms, especially in the domain of chemistry, which is one of the primary application of current generation quantum computing, a lot of chemical intuition is mapped to the quantum circuits, like bonds are mapped to entangling qubits. And that level of physics based modeling drastically enhances the modeling capabilities. And that is why we claim that as the number of qubits grow, we will be able to attain more accurate chemical simulations with quantum computers. It's because of utilizing the physics of the underlying system and mapping it to the physics of quantum algorithms or quantum circuits. So both things are possible, and typically for different applications, different types of techniques are used.
So here we are stopping the question answer session. And thank you, Mr. Lakshya, for this interesting and knowledge enriching lecture. Sir, if possible, could you please share the slides with us so that we can share this with our participants, if possible?
Yes, I will be able to share parts of it. I'll see what to share and get back by tomorrow.
Sure, sure, sir. Sure, sure. Okay. So once again, thank you so much, sir. Uh, okay, so for today's session, now we are closing. Tomorrow we will again start at 6 with Mr. Lakshya. Okay, thank you so much.